Now we're going to go and look at a few different types of equations and how we can use quadratic methods to solve them. So now that we've gone through all the different ways of solving quadratic equations, let's take a look at some times when we want to use each one. The very first method that we learned was factoring, followed by the square root property. These should always be our first two methods that we go to when we want to try and solve a quadratic equation. Now, the situation will vary depending on the type of quadratic we get. So with factoring, we want to try and use it anytime we can when our equation can be easily written in standard form of ax squared plus bx plus c. And a way that we can check whether or not we can factor is by using the discriminant. If the value of our discriminant is something that we can take the square root of, 0 or any perfect square, then that means that we can factor this polynomial. It's typically going to be faster and more efficient if we can factor the polynomial. The square root property is something that we can use only when we have the vertex form of the equation, or when there's only one term with a variable. If that's the case, then we want to get the squared term isolated, and then we can square root both sides to solve the quadratic. The third method we learned was completing the square. I'm going to put that one at the bottom, because this one's special. And then the last thing we learned was quadratic formula. Quadratic formula we want to use anytime the first two methods fail. So anytime that we cannot factor or use the square root property. Okay? Anytime we can't factor or use the square root property. So if our first go-to is, can I factor or can I use square root property? When both of those are no, then we use quadratic formula. And since quadratic formula always works, when do we use completing the square? And if the question we're asking is when to solve an equation by completing the square, the answer is never. Don't do it. You are not going to use completing the square to solve a quadratic, at least in my course, much further in the future. Completing the square is useful for other things, but we practice it when we are doing solving quadratics so that we have a solution that we can check the answer to. So the situation is, for this one, only when asked. Only when asked are we going to use completing the square. So let's go ahead and look at these equations. We've got a radical equation, rational, some polynomials, and different types of equations that will all eventually rely on quadratic methods for solving. So we're going to use our same process for solving these equations for previous units in order to start, and then we'll finish by using our quadratic methods at the end. So first we have a radical equation. We want to start by isolating our radical term. So we're going to go ahead and we are going to subtract x and add 6 to both sides. So we have negative square root of x equals negative x plus 6. The other way that we could do it is we could move the radical term instead, and we could add root 6 to both sides. And that'll again isolate it just to the other direction. Either of these processes will be fine. We'll still get the same result. Now, in order to get rid of the radical, we need to use our power rule. So we're going to square both sides, leaving us with x squared minus 12x plus 36 on the left, and then the radical cancels with x. So we're going to have x squared minus 13x plus 36 equals 0. Now that we're in standard form, we want to ask ourselves first and foremost, can we factor it? And yes, we can factor it because a product of 36 and a sum of negative 13 would be 9 and 4. So we can factor this to x minus 9 and x minus 4. Zero factor property, set these factors equal to 0, and then we solve, leaving us with x equals 9 and x equals 4. Now, because the original problem had a radical in it, it is a radical equation, meaning that we could have extraneous solutions. So we have to check our final answer to make sure that we don't have any extraneous values. So we'll start with 9. 9 minus the square root of 9 minus 6 equals 0. So we have 9 minus 3 minus 6. That's 6 minus 6, and that equals 0. So we know that 9 is a solution. It works. Let's try 4. 4 minus the square root of 4 minus 6 equals 0. So 4 minus 2 minus 6. 2 minus 6 does not equal 0. So we know that 4 is extraneous. So our only solution is x equals 9. Now moving on to a rational equation. We want to clear out the fraction by multiplying by the least common denominator. So everything's going to get multiplied by x minus 2. So the x minus 2 cancels in the first, the x in the second, and both terms in the third. So that's going to leave us with 3x squared minus x squared minus 2x plus x minus 2. We FOILed this here, 1, 2, 3, 4, and then equals 6. Let's distribute this negative after we combine like terms. This equals just negative x. So we're going to have 3x squared minus x squared plus x plus 2 equals 6. 2x squared plus x minus 4 equals 0 for our standard form. Now we want to ask ourselves, can we factor this? So we want to take a look and say any products of negative 8 that'll add to 1. If I try to multiply here, no, that's not going to work. I cannot factor it. Can I use the square root property? No, I have two variable terms, so I can't use the square root property. That leaves us with the quadratic formula. So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So negative 1 plus or minus the square root of 1 squared minus 4 times 2 times negative 4 all over 2 times 2. So x equals negative 1 plus or minus the square root of 1 plus 16, 32 over 4, leaving us with negative 1 plus or minus the square root of 33 over 4. So there's our two solutions. We just want to double check that neither of those values will make any of our denominators equal 0. Well, we know that x is not allowed to equal 2 and x is not allowed to equal 0. And so since this is neither 2 nor 0, we know that this solution is good. Now, this is not a quadratic equation, but is one that is quadratic in its form. And so we can still use the quadratic methods to solve it. And so here I have p to the fourth minus 3p squared minus 4. And this is actually something that I can factor because I have a product of negative 4 and a sum of negative 3. That's the numbers negative 4 and 1. So we can split this and then use our factor by grouping. So I'm going to split this into p to the fourth plus p squared minus 4p squared. I split this negative 3 into these two terms. Minus 4 equals 0. We can factor by grouping. P squared, leaving me with p squared plus 1, minus 4, leaving me with p squared plus 1. So we have p squared minus 4 and p squared plus 1. Using our zero factor property, we can set both of these factors equal to 0. And because we have in each of these equations only one squared term, that means we can use our square root property. So p squared equals 4. And when we square root both sides, p equals plus and minus 2. P squared equals negative 1. And when we square root both sides, p equals plus and minus the square root of negative 1, which is I. So our four solutions are positive and negative 2 and positive and negative I. Here we have a longer polynomial, and you might be tempted to expand this out, but again, notice that we have a structure here that again is quadratic in its nature. We have something squared minus something not squared, and then a constant without that term. So we can use our method of substitution. Let's let x minus 3 equal some other variable like y. And we can substitute y in for the expression x minus 3. So we have y squared minus 3y minus 4 equals 0. And then we can factor. We're going to have y minus 4 and y plus 1. And then we can go ahead and now that we have it factored, we can substitute the x minus 3 back into the equation. X minus 3 minus 4 and x minus 3 plus 1, leaving us with x minus 7 and x minus 2. Our zero factor property, that's going to leave us with x equals 7 and x equals 2. Lastly here, we have an equation with exponents. And again, we've got something that's really similar to a quadratic, but the fractional exponents are throwing us off a little bit. But we have something squared and we have something in the first power. We just have these denominators here. So let's again recall our power rule. X to the 2/3 is equivalent to 2 times 1/3, or 1/3 times 2. Using our power rule, since we have this multiplication, that means I have x to the 1/3 squared. And then here I have x to the 1/3. If we substitute x to the 1/3 with something else, let's say y, then that'll allow us to get a quadratic equation in its form. So x to the 1/3, so let's let x to the 1/3 equal y, and that'll then allow us to replace this as y squared minus 5y plus 6 equals 0. We want to ask ourselves, can we factor it? The answer is yes. We get y minus 3 and y minus 2 equals 0. And then we can go ahead and substitute back in now that it's factored. I have x to the 1/3 minus 3 and x to the 1/3 minus 2 equals 0. Our zero factor property, set these both equal to 0. We want to isolate. So I have x to the 1/3 equals 3, and I have x to the 1/3 equals 2. And then in order to get rid of the radical, we can use our power rule, which says we're going to cube both sides of the equation to get rid of the exponent of 1/3. 1/3 times 3 is just 1, so x equals 27 and x equals 8.